Yes, thank you for coming. And yes, I want to do a brief recap of what I said yesterday, because in particular I want to highlight some relations with Hilbert's theorem. So I will put Hilbert's theorem over here because I want to keep it. So yeah, so before we started by talking about globally non-negative polynomials, and then the first theorem of a kind was proved by Hilbert. So we said a polynomial, a non-negative polynomial, in n variables of degree 2d is always a sum of squares only in the following three cases. And then one was n is equal to 2. So not two variables, but this is two homogeneous variables. So one non-homogeneous variable, the other was degree is equal to 2. And there is a third case, n equals 3, 2d equals 4. Okay. And then we set out to generalize this theorem. And I said, so, instead of talking globally, but talking about globally non-negative polynomials, let's talk about polynomials that are non-negative on a projective variety. And then let's try to find the projective varieties for which we still have non-negative polynomials equal to sums of squares. All right, so that's the plan. So now, x inside Pn is a real projective variety. And then I said, so P sub x will be quadratic forms, non-negative on x, and sigma x are sums of squares of linear form. Okay, so maybe one thing that I should say, does it even make sense for me to talk about something being non-negative on a projective variety? Because, you cannot evaluate on a projective variety, right? Evaluation doesn't make sense. These things are equivalence classes, right? So let's make sure that this definition actually has some meaning to it. And the idea is like this. Well, of course, how do I take, so let's say, I will just write R coordinate ring of x. So what is that? That is just R is equal to, for me, over reals, so R x0 xn modulo the ideal of x. So let's say that I take, degree 2 quadratic form. Does it make sense, I take a point, let's say v in x. Well, it doesn't make sense for me to say what is f of v, but it does make sense for me to talk about the sign of f at v. Why is that? Well, because what should the sign be, right? Well, I should just take, the cone over x bar, which lives inside Rn plus 1. In other words, instead of thinking, x, the projective space is just the set of equivalence classes of lines. So take the cone. So take all of the points in the affine space that correspond to the points in the projective space. And now, I can take an affine representative of v. So I can take v bar, an affine representative. And of course, v bar, affine representative of v. And now, of course, I can evaluate f on v bar, right? That's not a problem. So what is the usual issue in these kind of things, right? So now I can talk about f being non-negative on v bar. right? But what is the usual issue in these kind of things? You know, what if I took another affine representative, right? Am I going to get the same sign or a different sign, right? So, you know, if I take another affine representative v double bar, well, it's just going to be some multiple of v bar. And then you can see, because f is homogeneous of degree 2, f of v double bar is just going to be lambda squared f of v bar. And, you know, as we know, squares are always non-negative, so we're not in trouble. Right, so it makes sense to talk about signs of forms of even degree on projective varieties, but for odd degree it just doesn't even make sense in this setup, right? But I just wanted to, I mean, this is kind of it's a technical point, but it's a good thing to understand, what exactly we're talking about. Right? So non-negativity makes sense. Questions, concerns, comments, ideas? Okay. And then I stated the theorem that you proved with Greg Smith and Mauricio Velasco, and said that non-negative polynomials are equal to sums of squares if and only if x is a variety of minimal degree. And then I needed to define what is a variety of minimal degree, and we discussed that for any variety, now thinking of this as a complex variety, so thinking of, this is the x is something that's defined by real equations, but I can also think of the complex points that are defined by these real equations, right? So I'm not only thinking about real points, but I'm thinking of x as having complex points that are defined by these real equations. So then, for any variety over C, it's true that the degree of x is at least codimension x plus 1. And if the equality holds, if degree of x is equal to codimension x plus 1, then x is a variety of minimal degree. All right. Great. And now, now I can move on and tell you actually. So what are varieties of minimal degree? Because they have been classified classically, at least over C. Okay. So Del Pezzo classified all surfaces of minimal degree, and then Bertini completed the classification. So X is a variety of minimal degree if and only if X is one of the following. So there's going to be a list that's not too long. So one, we already saw yesterday that if you have a hypersurface, then it has to be a quadric hypersurface, and that's one case. Two, this one I want to highlight. You have a Veronese embedding of P2 into P5, and I'm going to write out exactly what it is. So nu2, let me write it here. Nu2 P2 into P5. So the variety itself is just the embedding of all of P2, but what does it do? Nu2 takes x, y, z. I also wrote this yesterday. I will write this again, and sends it to, not good, so U2 takes x, y, z, and sends it to x squared, y squared, z squared, x, y, x, z, y, z. 3, it can be a rational normal scroll. That's sort of by far the most interesting family. And then 4, you can take a cone many times if you want. Okay, so what I would like to do is I would like to take this theorem, and now we know what the varieties of minimal degree are, and I want to look at Hilbert's theorem, and we should be able to see all of the cases of Hilbert's theorem in this theorem, in these two theorems, right? But perhaps they're hidden somewhere. For example, where is the case n is equal to 2? Right. Well, remember I said that, you know, because now n is equal to 2, but the degree is unlimited. Right? Degree is unlimited, and then I said that, you know, if you want to handle the case of polynomials of degree 2d, you just need to take the d-Veronese embedding. Right? So therefore, the case is equal n is equal to 2. For us, x should be the d-Veronese embedding of P1, and this is also known as a rational normal curve. And without saying too much about rational normal scrolls, I can tell you a rational normal curve is just one of this, is one of these. So 2d is equal to 2. Well, this is just the case where x is equal to just a projective space Pn. That's not interesting. In some sense, I don't know if it lies anywhere in here. Just slightly too trivial. Maybe you can say it's somehow inside a rational normal scroll somewhere. And then maybe the most interesting case. Where is this? Where is the case of ternary cortex? Well, again, this is degree 4, so we need to take the second Veronese embedding, right? So which means that x is exactly nu2 of P2, because we have 3 variables. And that is very interestingly, an exceptional case in Hilbert's theorem was also an exceptional case in the classification of varieties of minimal degree. Right. Right. So you have this exceptional Veronese surface. It's somehow exceptional here. It's I mean, these two are somehow infinite families, right? There is just one exceptional example, but it's also kind of quite interestingly an exceptional example here. Questions, concerns, comments? Okay, yeah, anything? All right, so so now let me talk a little bit. I mean, how would one prove something like this? I mean, in some sense, the proofs are not too hard, so I'm actually even going to present a complete proof of one of the directions of this theorem. It's not the proof that we found originally. But it's going to be very simple. But I guess I would say that the most interesting part here is actually finding the statement. I mean, once you find the correct statement, the proofs are not so bad. But finding the correct statement took a while. Okay. So how would you prove something? So what I want to show is that if x is not of minimal degree, then non-negative polynomials are not equal to sums of squares. I think in some sense that's the more interesting part, because we're excluding almost everything, right? We're excluding almost everything from the possible equality. The only thing that will be left are varieties of minimal degree, and then of course we need to show that the equality holds. So why would this be true? So let's begin by sort of making a trivial observation. Right, so we're going to make almost tautologies, but then once you put enough tautologies together, you get something that might not be entirely trivial. I mean, at least it seems that way. Okay, so what is the observation? So let's take a point P in X. Maybe P is a little confusing. Let's take point V in X. So suppose so we're going to go by contradiction. So we're going to assume that X is not of minimal degree, but we still have equality. Okay, so we will have P over P, so non-negative polynomials will be equal to sums of squares, but X is not of minimal degree. Okay, so suppose that, so we take point V in X, and suppose that we have F is in P sub X, which is the same as sigma X, same as sums of squares. And additionally, F of V is equal to 0. So we have a sum of squares. We have a non-negative polynomial, but because non-negative polynomials are equal to sums of squares, it is also a sum of squares, and it happens to be 0 at a point. Right? So I know that I can write F as the sum of Li squared, where Li's are linear forms. So then what can I say about every Li at V? Right. As I said, it's going to be trivial observations, right? They're not. So what can I say about every Li at V?
Right. They are all 0.
Yeah, they must be all 0, right? Then Li of V is equal to 0 for Li. Okay. So now let's keep this in mind, and maybe let's call this observation 1 and observation 2. So observation 2. So now let Y. So now again we'll take point V in X, and let Y be the projection away from P of X. This is projection away from P. Oh, that's P, this V. So I claim that P sub Y is still equal to sigma sub Y. I mean, if you want to make it sort of easier on yourselves, maybe you can coordinatize things in such a way that V is the point 1, 0, 0, 0, 0, 0, 0, 0. Okay? So what's happening here? Why should this be true? Well, how can I think of something that is non-negative, the non-negative polynomial on Y? Well, if I project away from this point, then I can think of this as having quadratic form on X, and then I just forget everything that depended on X0. Right? I just delete these things. Right? And so now, which means that if I want to write it, if I have f and p sub y, I can still think of it. I can still think, I can still think at f, or there is I could still think of f as lying on p sub x. In other words, what am I saying? I'm saying that y is the projection away from x, and this means that the coordinate ring of y, there is a natural, so we have a map pi v x y, and instead we have, this leads to maps of coordinate rings, right? R of y maps to R of x. Right. But I'm just trying to be informal here, right? So basically, I can think if f is something that's non-negative on the entire projection, of course it's going to be non-negative on x, right? If it is non-negative on x, I can write it as a sum of squares. F is in p sub x, then I can write f is equal to the sum of li squared. And because since f of v is equal to 0, you have, by observation 1, li of v is equal to 0 for all I. But what are linear forms that are 0 on v? What are linear forms that are 0 on v? These guys, linear forms that are 0 on v, are exactly linear functions on y. Right? That's by definition of projection away from point. Okay, so let's pause here and maybe I will entertain some questions. Because, once we understand this step, the rest of it is done. And there is not much more left to the proof. So I claim that if we have equality, if non-negative polynomials are equal to sums of squares, and you project away from a point, you still have equality. And why do I know this? Well, because if you have something that's not negative on y, it makes sense of me to think of it as a function on x. It's a function on x, it just does not depend on this coordinate, right? And because it's a function on x, I can write it as a sum of squares, and each of these sums of squares makes sense as a function on y, because it's also 0 at v. And that means that I should write it, which means, I guess maybe write like this, that f is in sigma y. And from that it follows that py is equal to sigma y. Questions, concerns, answers, objections? Okay, so now what is the third? What do we do next? Well, the third observation. Let's project many times. So now project away. Project away from codimension x minus 1 points. Let y be the image. Let's just make it doesn't matter too much, but let's just make the points generic. So what happens? So let's think about it. So we have x sitting inside Pn, and then we project away to y, and that sits inside. So we projected away codimension x many points, so this means that this is Pn n minus, so codimension x is n minus dim x. But we project away codimension x minus 1 many points, so this is P dim x plus 1. Okay, I'm just counting the dimensions here, right? So we have a variety y that sits inside P dim x, beside projective space of dimension dim x plus 1. Now, once we project away from points, of course, the dimension does not change, right? We have dimension y is equal to dimension x. So what does it say? It says that what we have is a hypersurface, right? We have a hypersurface here. Right, so something that's defined by one equation. So y is a hypersurface. Okay. Let's try to understand what is the degree of y. Well, every time we project away from point, we lose 1 from the degree. So the degree of y is equal to degree of x minus codimension x minus 1 is equal to degree of x minus codimension x plus 1. And now, let me just recall, if you have a variety of minimal degree, right, in the variety of minimal degree, degree of x is equal to codimension x minus 1, codimension x plus 1, which means that x was not a variety of minimal degree, which means that the degree of x was at least greater than or equal to codimension of x plus 2. Or in other words, degree of x minus codimension x was at least 2. And getting back here, which means this is a hypersurface of degree at least 3. Okay, so what are we saying here? All right, this is really the end. Because in fact, so y is a hypersurface of degree at least 3. So in fact, there are no quadrics in the ideal of y. Right? There are no quadrics in the ideal of y whatsoever. So then what is sigma y? Well, these are just quadratic polynomials. These are sums of squares of linear forms, modulo the ideal of y. But there is nothing, in degree 2 there is nothing. These are just sums of squares of linear forms. They are globally non-negative quadratic forms. Sigma y are globally non-negative quadratic forms. And this cannot possibly be equal to p sub y, right? Because, well, I mean, we can always construct, because you see, these are quadratic forms that are non-negative on y, right? But they don't have to be globally non-negative. They only need to be non-negative on whatever y is on this hypersurface, right? And it's easy to convince yourself that whatever whatever you try, whatever you define, you can always build a quadratic form. Just think of taking a point and sort of building a tiny ball around it, right? That's kind of the affine picture, right? Building a quadratic form like this, right? It's going to be negative at this point, and negative, inside this ball, but then positive everywhere else, right? That's something that's going to be in p sub y, but it's not going to be in sigma y because there is nothing in the ideal, right? P sub y, these are quadratic forms non-negative on y. And these two are obviously not equal. And that is a contradiction. So as I said, these are really, I mean, we took three, I would say, very simple statement, right? This is almost nothing. Just says that, you know, if you have something that's 0 and it's a sum of, that's 0 at the point, it's a sum of squares, everything needs to vanish. And then we took this observation and we sort of bumped it up into projection away from points. Then we say, well, if you project away from enough points, you will arrive at something where there are no quadrics in the ideal whatsoever. And then non-negative polynomials cannot possibly be equal to sums of squares. And that's a contradiction. Questions?
Can you explain
Yes.
the last part?
Oh, the last, so you mean why are these two not equal? Yeah, so the idea is that, you see, because there are no quadrics in the ideal of y, what are sums of squares on y? Well, these are just sums of squares of linear forms, modulo the ideal of y. But ideal of y doesn't have anything in degree 2. So I don't have anything to mod out. So whatever is a sum of squares on y is just sum of the squares of linear forms. So such a thing is going to be greater than or equal to 0 everywhere. Right? It just doesn't have a choice. It's a sum of squares of linear forms. Right? But what are p-sub-i? These are quadratic forms that are non-negative on y. And we can build a quadratic form that is non-negative on y, but not non-negative everywhere. I said, as I just said, they take a point that's not in y and define just, you know, the tiny ball around it with the distance to this point, right? And, you know, it's going to be sort of negative at the point, make it so it's negative at the point, and it's negative inside the ball, and then it's, you know, and then it's 0 on the surface, and then it's positive everywhere else. And you will see that this is because this is point not on y. It's going to be non-negative on y, but it's not non-negative everywhere. In fact, it's negative at the center of the ball, right? So you can easily build quadratic forms that are not globally non-negative, but non-negative on y. And that's a problem, right? Because by our logic, we should have had equality, and that's a contradiction. So as I said, that's not the original proof that we had, but I think this is the easiest one that I've found so far. Okay, shall we move on? Is that okay? All right. So now I want to talk a little bit about about duality, basically, and about another idea that was actually quite crucial in the history of non-negative polynomials and sums of squares. And that is actually the relation of all of these things to analysis. Because you see polynomials, you know, is polynomial really an algebraic object or is it an analytic object? You know, people might disagree reasonably where do these things belong. And actually non-negative polynomials are also important in analysis because of the following. Okay, so this will go under the name of moment problems, and I will try to explain what a moment is and so on, and then I will explain what does this have to do with duality. But essentially, okay. So what is the idea here? So now actually I'm very sad that I'm going to have to switch, and I'm going to work with non-homogeneous polynomials. So from now on, for a little while at least, I'm going to talk about polynomials that are not homogeneous. Okay, but I'm going to write Rx less than or equal to 2D for all polynomials in n variables of degree at most 2D. Okay. So now the kind of question that we will want to answer is like this. So let's say that I will give you a linear functional L on this vector space. So it's something that's, it's a linear thing that eats a polynomial and gives me a number. And what we will want to ask, what one might wonder is, does L come from a measure? What does this mean? Does this mean, so this means, can I write L of f as integral of f d mu, where mu is some, Borel measure on Rn? So if I give you a linear functional, so something that's linear, eats polynomials, returns real numbers, right? Yeah, and you might want to know, does this thing, is there an underlying measure that represents this linear functional? So what would be an obvious necessary condition to come from a measure? What would be an obvious necessary condition? So what happens, if you come from a measure and you eat a non-negative polynomial, what must you output? Right. So what I'm saying is that, let's say that L, if L does come from a measure, and I take f, a non-negative polynomial, so I will write it p n maybe less than or equal to d. That's right. Then you know that L of f better be non-negative. Right? I mean, there is no question about that. And essentially, okay, but then you might wonder, is this in fact sufficient? Right? If I have a functional that for every non-negative polynomial gives me a non-negative output, does it come from a measure? So the answer in this case, if we work non-homogeneously, the answer is almost correct. It's almost yes. There's some technical issues with this, but it's almost always true. So this obvious necessary condition is sort of nearly sufficient. I don't want to make it too precise. There are some rare cases where even though if you're non-negative or non-negative polynomials, you will not come from a measure. But almost always this is enough. And so what is this really saying? It is really saying that non-negative polynomials are dual to measures. Okay, so what does this mean? Let me make this statement more precise. So as I said, we have this vector space. I erased it. Rx less than or equal to 2d. These are polynomials of degree at most 2d. Inside this vector space, there lives the cone of non-negative polynomials of degree at most 2D. And now we have a dual vector space. The dual vector space, what is this? This is just vector space of all functionals, linear functionals. Less than or equal to. And inside this space, there lives another thing. I will call it maybe M and 2D. This is the set of all functionals. All functionals that come from a measure. And I will, now I will make this nearly sufficient, essentially precise, and I will also make the statement dual to measures, also more or less precise. Okay, so again, let's think about this. This guy, non-negative polynomials of degree at most 2D, this is a convex cone. Linear functionals that come from a measure, is this also a convex cone? Well, when you think about it, you have two linear functions, one comes from a measure and another comes from a measure. You can just, take these measures, add them to each other, and you'll have another linear functional that comes from the sum. So this is also a convex cone. And what is the relationship between these cones? So let's say I will write down a proposition, which I will not prove. So this guy happens to be, maybe let me define, I need to define something. What is a dual? What is a dual cone? Dual cone, I need to define a dual cone. So let me just, so this is duality within convex geometry, which is also not too different from duality within algebraic geometry, if you look at it in the right way. So let's say we have K is a convex cone in a finite dimensional vector space. So then what is the dual cone K star? Well, K star lives inside the dual vector space V star, which is all linear functionals on V. So I just want to say that if your vector space V is not finite dimensional, you have to be careful. The dual space is not the space of all linear functionals, because not all linear functionals are nice. You need to take the continuous ones or bounded ones, which is equivalent. But because we're dealing with a finite dimensional vector space, there are no issues, right? I'm not sweeping anything under the carpet. Okay, so what is K star? So K star is just the set of all linear functionals in V star such that L of P is greater than or equal to 0 for all P in K. Let me try to explain what is the idea of the dual cone. Just sort of intuitively what's happening here. So duality in convex geometry is a very powerful idea. So what's happening here? What is the idea? Well, if you have a convex set like this notepad, it can, you can think of it like this, just as a set of points that happens to be convex. But you can also think of it as being defined by some inequalities. right? Like this is greater than or equal to 0, 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 right? And what the dual cone does is it collects all of the valid inequalities, right? So this is one. So there are two ways of looking at the convex set. One way to think of it is just, well, here it is, or you can think, well, it's defined. This one is defined by finitely many inequalities. That's why it's a polyhedral cone. If you have a convex cone, it could also be defined by infinitely many inequalities, right? But you collect all of these inequalities together, and you somehow you have another convex cone, and that convex cone is called the dual cone. Okay, and yeah, so now let me state a proposition and maybe discuss it a little bit, and then we will be out of time. So proposition. So we have these two cones, P n less than or equal to 2D and M and 2D. What do you think should be the relationship between these two cones? Right. So I know that if I take a linear functional here and I apply it to anything here, I'm going to get something non-negative. Right. In fact, so this means that this guy lives inside the dual cone of that. Right. That's basically by definition. Right. But in fact, it should be right, it's a little bit stronger than that. That's why I said that the necessary condition is also sufficient. So let me write it like this. So P and 2D star, so the dual cone to the cone of non-negative polynomials, it's not quite equal to M and 2D, but it's equal to its closure. Because you see, somehow it happens that this cone is not closed. That's sort of, it's one sort of not very nice feature. And the dual of a cone, you can just check from definition, is always closed. It's always a closed cone. And but if you go the other way, so P n less than or equal to 2D is equal to, in this case, there is no need to take closure. Right. So this is what I mean, that the non-negative polynomials are dual to measures. This provides connection to real analysis. And that it's kind of almost true. It's almost exactly what you want. There is this slight closure problem, but most of the time one doesn't need to worry too much about that. Okay, so maybe let me just say, you know, I call these things moment problems, and I never explain what is moment. So the idea is that if you give me a linear functional on the space of polynomials, and so it's in the dual space, one way to represent it is to evaluate the functional on the basis. Right? I can just evaluate L on all of the monomials, right, and give me a full list. And if L came from a measure, then integral of a monomial with respect to the measure, this is what is called a moment. So this is why in the literature, when you see it, usually they will say, given a moment sequence, meaning given this long list of all of the values, does this moment sequence come from a measure? To me, this is just a little bit ugly way of posing the question, because in the end, you're giving a linear functional, right? You do not need to be very much attached to a specific basis on which you're evaluating. But that's why these things are called moment problems, because what they say is, well, given a list of possible moments, can you tell, do these moments come from a measure? And if they do come from a measure, then you might be interested, what is that measure? You know, can you reconstruct the measure? Right. And also you can do this, you know, not just finite dimension. You could say you have an infinite list of moments. So I give you all of the moments, right, on all of the polynomials. And in this case, the situation is even better. In a sense, so that this, if you do the duality correctly, there is no need to take closure and so on. But in any case, and this, yeah, I mean, this connection with real analysis played an important role in the development of the subject, because some of the theorems in real algebraic geometry about non-negative polynomials were proved by people from analysis who were interested in finding out when do functionals come from a measure. Okay, I think that's as much as I can say because I'm out of time, so thank you for your attention.